All right, well, hi everybody. I apologize for that little delay, but my name is Raymond Clay. I'm here to talk to you about some of the new and upcoming features in QMCPACK. So this talk is going to be focusing on two major classes of code developments. The first is going to be ways to compute certain types of energy derivatives in QMC, and the second will be talking about ways to improve your trial wave function through orbital optimization, which has been alluded to previously in this workshop. So we'll start with the first case. And so why do we care about energy derivatives? Well, since we're working basically with electronic potential energy surface, there are certain features that we would like to be able to identify and classify, specifically minima. Minima are important because not only do you need this for a starting point in structure optimization or structure searching, but much of the elastic properties of materials are determined by basically understanding the perturbations of your potential energy surface around your local minima. So understanding the second derivatives within the quasi-harmonic approximation, you can actually get full-blown phonon spectra. So that's useful, that's nice. And so DFT is DFT is pretty much the workhorse in these sorts of calculations. It's a pretty nice balance between being reasonably efficient and being reasonably accurate. So most of the major structure sort of searching programs are done using DFT as a base. And additionally, DFT is used pretty heavily in things like quantum molecular dynamics and its various generalizations. So what we'd like to use, or what we'd like to do, is use QMC in many of these applications because of its superior accuracy in quite a few applications. And this is not just an academic sort of concern, you know, like there will be many arguments in the literature about, well, you know, we might not be good for energies or we might not be good for pressures, but a lot of these differences between structural energies and stuff cancel out. You know, the DFT structures might be fine, but this is an example of a sort of a benchmarking study we did in dense hydrogen. So there is a very special sort of phase transition above about 200 GPa in dense hydrogen, whereby you have a crystal of H2 molecules suddenly dissociate into a crystal of hydrogen atoms. And so if you want to start talking about things like where does the insulator to metal transition happen in hydrogen, you know, what's superconductivity like on the other side of that transition, you really need the right structure, just, you know, step zero. But what I'm showing in this plot over here is, all right, there we are. So what I'm showing in this plot is pretty much the the enthalpy calculated by QMC as a function of pressure. And what I've done is I have calculated these enthalpies for several of the proposed hydrogen structures. So the different colors are different structures, and the dashed lines and the solid lines are basically where did I get my structures from? Did I get it from a PBE optimization? Did I get it from a van der Waals DF optimization? And so one of the things you'll notice is like not only are all these lines shifted by between half a millihartree to a millihartree, but many of these errors are not self-canceling. Particularly over here, you would expect these two structures to become degenerate using DFT structures within the van der Waals DF framework, but over here, the difference is over half a millihartree, which is pretty fatal given the enthalpy scales here for these sorts of phase transitions. So I'm going to introduce you to sort of how we deal with these energy derivatives, first of all, by just giving you the definition so we can start rolling with it. So pretty much you guys all know force, negative gradient of the energy. And stress, for people who don't do materials properties, is a little trickier to understand, but basically you're looking at how the energy changes as your unit cell is either compressed along various axes or it's sheared. So, okay. So what's the problem with just calculating these things immediately in QMC? Well, the takeaway message for most of this conference has been the fact QMC is a stochastic method. Any quantity that you come up with, or unless you have the perfect wave function, is going to come with an associated error bar. So let's say I want to compute the force on an atom. Let's say that this might be the bond distance between like a carbon atom or something, and this might be the energy as a function of the distance. So you'll notice that like there's a trade-off between the systematic sort of error coming from the size of your finite differencing sort of estimate, and also the statistical error that's introduced into your derivative estimate. So over here, you can see the derivative is probably going to be anywhere in the shaded region over here. If I bring these significantly closer, I'm going to reduce the systematic errors for my using my finite difference formula, but then my slope could probably even be positive, negative, or whatever I want it to be. And there are obviously tricks for dealing with this sort of like, with these error bars, but even so, it's a pretty expensive sort of procedure if you want to flush it through to its conclusions. I mean, if I had to compute the forces in a realistic unit cell, we're talking about 3n different force components, which is on the order of 3n simulations. So, quantum chemists have known this for a while. This is a pretty basic theorem, but we don't have to do finite differences in electronic structure theory. I mean, pretty much as long as psi is an eigenstate or a variational minima, you can show that the derivative energy, or the derivative of the energy with respect to any sort of parameter in your Hamiltonian is just going to be the expectation value of the derivative of your Hamiltonian. So we call these Hellman-Feynman estimators, which is great, but we just have to make sure before we blindly stumble forward that like these estimators have the right analytic properties to enable us to put an error bar on them. And unfortunately, forces are not one of these things where right off the bat, that's going to be something you can do. So what I've done here is I've shown you a brief expression for the expectation value of the force around a single ion. So this is a simplification, obviously, but you'll notice that like you don't really have to know what the charge density is. I mean, as long as it's reasonable. But you can show that this integral over here exists. The mean value of the force is well defined, but you pop down here and let's say we want to estimate the expectation value of force component squared, which you need for the variance, and you'll notice that this has a divergence. In fact, it diverges like 1 over r squared. So this is an infinite variance estimator. So there are several tricks. The one that is in the code was pretty much invented by David and collaborators, which basically it identifies the source of the divergence in QMC, which is basically like the S wave, or so the S wave component of the density, which is basically the spherically symmetric part. If you decompose the density into its various angular momentum components, is going to be the term with the divergent piece in it, but it contributes nothing to the expectation value of this force. So basically, by sort of adding a weighting function within a certain cutoff radius over here, then you can basically eliminate this divergence, get a finite variance estimator, and actually drop the variance to something workable. So there are several parameters in here. Obviously, you have the degree of the polynomial that you want for this function. You have some sort of weighting factor over here. It's usually chosen to be 2. And of course, you have the cutoff radius over here. Now, this whole thing was derived just assuming that your charge density is physical. You don't have any like crazy discontinuity. No, you don't have discontinuities in your density. And what's cool about this is that this is totally analytically determined. Like there's no free parameters. Like you give me a cutoff radius, a degree of a polynomial, and this weighting factor, and all these are determined off the bat. So some disadvantages: it's not zero variance like the energy. It's not zero bias, but it is systematically improvable just by increasing the values of these parameters. So you can understand both the systematic and statistical errors. So this is currently in the code right now. It's a very easy sort of tag you can put in here where these are all the parameters I talked about. N basis is pretty much the degree of your polynomial, and this weight exponent, just leave it at 2, unless you have compelling reasons to do otherwise. And of course, it'll show up in the scalar.dat file like all your other observables. So anyways, we've done several tests of this. One of the first things I did was comparing this estimator against finite differences. We just picked 4 hydrogen atoms, squeezed them together. And that is not good. Okay. Well, you can take my word for it. That figure was amazing. But yeah, it's basically, there's a small systematic bias, but it was about 0.15% error off of the finite difference results. So it's pretty good there. What's up? Okay. So, what was I talking about? I was talking about forces. So anyways, we also did finite difference tests in bulk calculations, particularly like in these hydrogen-helium mixtures. You know, you grab an atom, randomly perturb it, and once that held up very well, we decided to use these forces in sort of benchmarking applications and bulk hydrogen-helium calculations. And what's really cool about this is that you know, we've mentioned using QMC for benchmarking, you know, like in benchmarking van der Waals interactions, S22s, but for the most part, you really only get an energy, maybe a pressure out of it. But having access to these forces gives you a quite impressive amount of resolution in terms of finding out where your functional is breaking down, what it's failing to capture. And so what I've done here is I've shown the average force error between the hydrogen atoms as a function of distance. And these are just a ton of different functionals, but you'll notice that some of these functionals, like let's say van der Waals dF2, overbinds extremely heavily in a small region kind of near the hydrogen atoms, whereas some others like LDA, PBE significantly underbind, which, okay, that's nice, but it also allows us to tell, like, you know, which sort of functionals are giving us a reasonable description of the charge density, and which is great. Also, you know, we can run through for pretty much every pair of interactions, at least for these low Z sort of materials. So yeah, an example of like how many atoms these things had. This was at a pretty high density, probably well over like 300, 400 GPa, and there were like 64 atoms in it. So, you know, it's non-trivial. So this key is a perley-Zhang sort of estimator. It's got some advantages. It's simple, it's accurate, and it's efficient for light elements. It is a mixed estimator, but, you know, that's something you have to kind of deal with in QMC. But more troubling is the idea that, like, this thing does not really have a favorable scaling with atomic numbers. So, you know, you might be able to get to lithium or maybe something higher, but before too long, your error bars are going to kill you. So, so when it comes to stress, let me see here. Basically, crunching through the Hellman-Feynman sort of formulation, you can pretty much come up with this estimator. Now, this has some pretty nice little analytic properties, namely its finite variance, which is very nice. We don't have to figure out how to, like, how to really tweak it or fix it on a fundamental level. And this thing currently works in the code. So if it doesn't, let me know. I will make sure it's working. It was working not too long ago. So disadvantage here is it works for all electron calculations, but that's about it. Also pseudopotentials, not yet. Not hard, you just need to specify these derivatives, but they're a little bit of a bear. So using stress estimator, that's fine, very straightforward. No adjustable parameters, it's even better. Okay, and this is just a sort of quick test and everything. So these are finite size corrected estimates, and they were extrapolated to remove the mixed estimator bias. All of these values were checked against finite differencing and found to be spot on within the error bars. So this is this was taken on a liquid snapshot from hydrogen. So it's got about 54 atoms in it, about 100-ish GPa. But what you'll notice though is that, I mean, some of these functions do pretty well. I mean, LDA and HSE are obviously are really good for these, whereas some of the other ones aren't. So fortunately, it's a consistent sort of picture we got before, but it's just a lot more information. So, okay. So forces are nice, stresses are nice. While we don't have estimators for the second derivatives, it's a whole lot easier to construct a bunch of second derivatives from a pile of first derivatives like they do in the phonon calculations. So, so that would be one thing you could do with this. Additionally, like, having the forces right out of quantum Monte Carlo opens up the possibility of doing things like molecular dynamics and stuff. So basically, we're kind of flushing through the applications slowly but surely. So the other main feature, this is significantly more simple, is orbital optimization. And so what I'd like to do is I'd like to remind you all of the Slater-Jastrow form. I'm using one component for simplicity, but most of this talk has been discussing how to optimize this guy. What are the forms? What are the different interactions you throw in? But you might ask the question, it's like, well, why not optimize these guys? And of course, there are some pretty big advantages to doing this. I mean, for the most part, the charge density is determined by the orbitals you get out of a mean field theory, but more importantly, your nodal surface is pretty much exclusively determined by these orbitals. So, which is fine and all, you might be like, well, mean field theories give you a pretty okay description of the nodal surface, but there are known cases like various magnetic transitions between, let's say, a paramagnetic and antiferromagnetic state where your LDA or even your GGA is not guaranteed to give you an antiferromagnetic state. So if you didn't know that, and if you couldn't construct your antiferromagnetic state by hand, the accuracy of your QMC would be very suspect at that point. So, I mean, DMC can only go so far in correcting a really bad guess. And then, obviously smaller energies and variances and everything else. But when this is generalized to multi-determinants, the advantages over here start becoming pretty, there are way more advantages in the multi-determinant case because basically we have a paper studying sort of like how compact your multi-determinant expansion is based on the choice of orbitals, and there is a noticeable degree of sensitivity. Like if you start off with bad orbitals, you're going to be using way more multi-determinants to compensate for a bad guess. So out of computational efficiency and accuracy, we need to be able to do this. So this is just an example of sensitivity of sort of two different magnetic states in is that magnesium oxide? Yeah. No, manganese oxide. Okay, ignore that. So this is just, they take a hybrid functional and change the mixing fraction over here. But you notice that there, let's say you start off at 0.2, there is a noticeable decline in energy just by tweaking this. And so if it's already exhibiting sensitivity to, if the DMC energy is already exhibiting sensitivity to the orbitals here, how much do you think you could gain from a more general sort of optimization framework? So what is implemented in the code is, works as follows. Instead of optimizing parameters within the independent orbitals, what we do is we take our entire orbital set, arrange it in order based on energy, and what I have over here are basically occupied orbitals. So we would build a single determinant out of this, and we have a bunch of other orbitals that we call the virtuals. And so what we do is we declare a certain piece of this orbital space as sort of our active space. And then what we do is we construct a unitary transformation to perform orbital rotations basically mixing these orbitals in with these and vice versa. So instead of optimizing the orbitals themselves, what we're doing is we're optimizing the components of this rotation matrix. And so this has some pretty nice advantages. I mean, you don't have to worry about messing up the orthonormality of your orbitals. It also it treats the single Slater and multi-Slater determinants on the same sort of level. Additionally, the analytic derivatives are much more straightforward than if you had a sort of, complicated orbital form or something like that. So what's going to be coming down the pipeline in probably by the next release is single Slater determinant optimization, and so that's going to be so that's going to be within this restricted and unrestricted sort of orbital framework for people who are used to DFT, sorry, quantum chemistry, and currently the code works with local pseudopotentials. It's going to need to be generalized a little bit for the non-local pieces, but that's okay. And it's currently working in open and periodic boundary conditions. So a lot's been done already, but again, we have to include non-local pseudopotentials. And the multi-determinants are coming, but that's way further down the pipeline. So conclusions, there's a lot of cool features we put in. Hope you get to use them soon. And I'd like to thank my advisor, David, and my Livermore advisor, Miguel Morales, and the entire QMCPACK team for maintaining the code, collaborating, and just for homework and future reading and everything else. I think Carlo did a good job explaining sort of the using quantum Monte Carlo for things like molecular dynamics, but basically I would point you to this structural optimization paper with QMC for things that are coming down the pipeline. So anyways, not too bad on time. Questions? Yes.
How was the active space chosen?
You said it. I mean, this is really more to do the orbital rotation. I mean, we're not building a CAS or anything here.
Right. So is it energy criteria, like homolumo?
Energy criteria. You specify. It's once it's ordered, it's like anything above these 4 orbitals, at the bottom of the occupieds, and all the way up to this many orbitals in the virtuals. Yes.
I have a very quick question about the Feynman Theorem. So in the optimization of the VMC calculation, I remember that we use a cost function. The cost function is a mixture of energy and variance, right? So if we optimize variance, the Hamiltonian is different. So the Feynman Theorem will not give you pure force, but there is some mixture of the derivative of the variance operator.
Yeah.
So how do you deal with that?
Well, if you want to be rigorous, I would optimize with, so the variances include just for stability. And honestly, once you have nearly the right wave function, you can just turn off that, variance mixing and just have a pure energy optimization run.
Okay.
So.
And also, since if you are using the DFT as a trial wave function,
yeah,
then you also inherited something like the Poulet force, the Poulet errors, right?
So if we were using localized basis sets, we would certainly have to include that. Yeah, but for the plane waves and stuff, I mean, basically the first contribution, that's 0. So.
Okay, thanks.